Okay, so I mentioned before that a group will essentially be a way that you can mathematically encode what a symmetry is. Okay, so to give you a better idea of what I mean by that, so suppose that I pose this question. So suppose two people wanted to understand the symmetry of an equilateral triangle. So I give you an equilateral triangle. Person one basically is going to look at the initial position of the triangle and look away. So suppose that you just have this triangle, but you don't have anything labeled on the triangle, but you look away, and person two takes that triangle and they're allowed to move it any way that they want and put it down in a position, put it back on the table so that when person one looks back at it, it effectively looks like it's in the same position, but they might have manipulated it in some way, right? Maybe reflect it, rotate it, or maybe done nothing at all, right? So that's what we mean by a symmetry. What are some ways that you can take an object and you can manipulate it in some way that it will effectively look like you almost did nothing to it? Okay. Now, so how many ways can this be done? Now, it seems like there's going to be an infinite number of ways that you can do it, because you could just say, oh, let's rotate it, as many times as you want and put it down. But fundamentally, are there some basic motions that we can perform so that all the more general ones that you could come up with can be encoded using those basic manipulations? Okay, so in order to represent this mathematically, what we could do is you can take your equilateral triangle and we can label the vertices. Okay, so let's label them 1, 2, 3. And suppose that you're able to manipulate the triangle. And suppose that the 1, 2, and 3 are in those positions if you were to like reverse it to the other side. Okay, so one basic motion that you could do is you could rotate it by 0 degrees. So if I took this triangle, did nothing to it, you would get back, well, the same triangle in the same positions possible, right? Another way that you could do this is you could rotate it by 120 degrees. So we could denote the angle at which you're going to rotate it in degrees as sort of a subscript here. So if I rotate it by 120 degrees, using classical convention that, you know how in geometry you learn rotations usually do those counterclockwise. So let's say that you took this triangle, you rotated it 120 degrees counterclockwise, then what's going to happen to the position of these numbers? So vertex 1 will move into the position of where vertex 2 is, and vertex 2 will move into the position of where vertex 3 is, and 3 will go to 1. So you see, you would get this triangle. Of course, you would actually have a rotated labeling there, but I'm just, the numbers are kind of just telling you where that vertex was and where it ends up, okay? So do you guys agree that if you rotated by 120 degrees, it would look like this? So 1 would go to 2, 2 would go to 3, and 3 would go to 1. Right? Similarly, you can actually rotate it by 240 degrees, and then 1 would go to the position of 3, which we see here. 2 would go to the position of 1, right? That's why it's up here. And then 3 would go to the position of 2. So we'd end up in this situation. Now, any of the other rotations you can think of where you would pick up this thing and you would rotate it any number of ways would just be a combination of these basic rotations. So for example, if you rotated it 360 degrees, it would effectively do the same thing as rotating it by 0. And if you chose some other angle, let's say by 60, then you're not going to get remember, you have to be able to pick this up and rotate it, and effectively it has to look as if what it originally looked like. So 60 degrees would sort of be it won't look exactly in that right way. So the rotations, anything that's obtained by rotations should be a combination of those ones. So doing nothing, or rotate by 120 degrees, or 240. Now, notice that you can actually get R240 from R120. Like R120 could generate that rotation as well. I could just do that one twice, right? So you might ask, are there some basic members of this collection that will be able to get us to all the other ones? Right? So another thing that you...
That's all talking like counterclockwise, right? Could you go counterclockwise too with that?
Yeah, so if you did a clockwise rotation of 120, that would actually be the same as the R240, right?
Yeah.
So we don't have to really distinguish what we did because you're only really just looking at what is the state at the beginning and what is the state at the end. So there was something that you did intermediate to get you to the final state, but really to encode this symmetry, so to speak, all you care about is what's happening at the beginning and at the end, if that kind of makes sense. Now, if you're working on a more complicated problem, which may happen in an application, you actually have to pay attention to what's happening at the in the middle. An example that might be like a function, right? A function, you give me an input, I give you an output, but it doesn't really, you don't really have to pay attention to what's happening in between the input and the output. You don't have to know the inner workings of that, like a black box, right? You send the input in and the box gives you an output. But sometimes there may be an application where you actually have to know the fundamentals of what's happening inside the box, right? So it's kind of similar here. We don't have to actually know what is getting us to the final output, just what are all the possible outputs in a way. Yeah, if that's okay. So your idea would give you an equivalent output. So we would just kind of treat that as the same. Yeah. Yeah. It's almost as if you have an infinite collection and you're sort of, you got these classes, so to speak, kind of similar to the idea of like equivalence classes. We would treat those as all equivalent in some way. You can also do reflections, right? So if I were to put sort of a mirror down the middle of this and I were to reflect across this dotted line here, then one would stay in the same position. But then if I reflect this over that dotted line, then 2 and 3 would interchange position. So I use the letter N here as if it's sort of like a north, I don't know, north reflection. And also you get a silly pun that if you do east and west, then this is a new concept, right? So yeah. So you could also put your mirror this way. So it goes from vertex to the center of this edge. And now 2 will stay fixed, right? If you reflect, but then 1 and 3 will interchange positions. And then you could also have sort of your mirror here, and 1 and 2 will get swapped, but 3 will stay the same. Okay, so it looks like we're going to have 3 rotations and 3 reflections, right? And then any other type of symmetry should be some kind of combination of these sort of fundamental ones, right? So one thing we should ask now is if we combine the motions above together, is any sequence of motions one of these 6? So let's take a closer look at what's going on. And look at what happens when we combine these. So if I were to reflect by my reflection N, so 2 and 3 get swapped. And let's say that I did it again, 2 and 3 get swapped. Notice that doing that reflection twice is actually going to be equivalent to doing nothing, actually, doing a rotation by 0 degrees. So you kind of have a way of representing, either you can think of it as like a multiplication or you can think of it as a function composition, right? You're doing this north reflection twice and you get back the another element, another basic motion, which is R0. Similarly, let's say that you did this north reflection, so 2 and 3 get swapped, right? And then now you take this new triangle, and then you did a rotation by 120 degrees counterclockwise. So now 1 will go into this position, 2 will go up here, and 3 will go here. And then if you just look at the beginning and the end, and you ignore the middle, okay? If you ignore what's happening in the middle, and you just look at the beginning and the end, and you look up here, you could just ask, okay, are any of those output triangles the same? And if they are, then you're pretty much just saying that if I do both of those, it's going to be the same as doing one of these basic ones. And if you stare at it a little bit, the one that has a 2 and then a 1 and a 3 is this one, right? 2, 1, 3. Right? So 2, 1, 3 matches my 2, 1, 3. So it looks like doing north reflection and a rotation by 120 should be the same as doing a I guess the west, right? The reflection across along that line. Okay, so you see, it should remind you either of multiplication or probably more so of function composition, right? It's as if you're doing that function and this function, you can kind of just say that it's the composition of those two. So this is good. This is kind of saying that I have a method of combining my rotations and I will get back a rotation. That idea right there is what's called a binary operation. You're kind of giving me two inputs, and I'll give you an output, and it stays one of these fundamental rotations or reflections. In other words, I'm not getting anything that I'm missing from that list. If you were to combine these two and you were to get something new, then we should add to that list. We should add some new magical rotation or reflection, or maybe some other symmetry, which may happen. You might have guessed this collection, but are there any others? And one way to try and see if there are others are combining these in any way and seeing if you get something new. Okay, one way that you can really organize this in a neat way is you could look at all the possible combinations of these. Okay, so what you can do is we could find all the possible pairwise multiplications or these function compositions. And since there were 6 of these, right, originally, I could take any 6 of these and combine it with any of the 6. So I should actually have a total of 36 possible ways to combine them, right? And what you can build is this nice multiplication table. You can either call it a multiplication table. In group theory, this is usually called a Cayley table, right? After Arthur Cayley, mathematician. So to compute motion A followed by motion B, written like this, just thinking of it as function composition, really all you're just going to do is just think of it as take an element in one of these rows and think of it as multiplying it as one of the elements in this column, and whatever's in the table, that's like your output, which you're familiar with, right? Just like when you learn how to multiply numbers, right, from 1 to 10, right? I believe we did that at some point back in the day. Don't you remember like a multiplication table or an addition table back in the day, right? So you look up at the table to see the corresponding value. So for example, the 2 that we have right here, you can see them in the table, right? So n times n, or n compose n, whatever way you want to think of it as, you see n and n will give you the, right? So you just follow row for n. This is n times r0, n times r120, n times r240, and then n times n will be in precisely the entry where the row and the column meet together, and that's exactly what we have here. So you see, you have some color pencil or pen to denote this. So that's where it appears in the table. And then this one, let's do R120 by N. So R120 followed by N will give us this W. Right? And you could sit down and try to draw all 36 of those, but kind of giving you the answer right here by filling in this table. But the nice thing that you should notice, well, there's a few properties that are kind of interesting looking at this table. For one, every single one of these outputs is one of these 6 fundamental rotations or reflections. You see that no matter how I combined them, I didn't end up with something that was new, okay? And if you did, what that means is your table is either incomplete or something went wrong. Okay, if it's incomplete, then that would mean that you probably would need to add a row and a column to this with that new fundamental rotation or reflection or whatever it may be, and then you could try to fix it. Okay, but what's this? If your outputs, if you take 2 elements from a set and you combine them together in some way, and then you get back something in the set, that is what's called a closure property, or what you're really saying is you have a binary operation. So binary meaning 2, you give me 2 elements from your set, you combine them in some nice way, and if you get back something in the set, then we call that a binary operation. Okay, so every single group that we deal with in this course, that's one fundamental property we have to have. We have to have what's called closure. It has to, if I give you 2 elements of my set and I combine them using my operation, I have to stay inside the set. So notice that this table is filled with no new rotations. So this means that any sequence of motions must be one of these 6. And this is the property of closure. Okay. And I'll tell you in the next note set that we're also calling this that you have a binary operation. Okay, now this set of 6 motions together with that operation of composition forms a special kind of group, and what it's called is the dihedral group of order 6. Okay, and we denote it as D sub 3 because it describes the symmetries of an equilateral triangle, otherwise known as a regular three-gon. But I'm sure you guys don't ever call it a regular three-gon. You probably call it a regular triangle. Just like a square would be a regular four-gon, a pentagon would be a regular five-gon, and so on and so on. What were you going to say? Sorry. Yeah. Yeah, that'd be kind of annoying, right? I mean, you just have this terminology in the event that, yeah, Fallon's saying she always calls it a regular three-gon.
Shape, like you can say a regular 20-gon, and that's acceptable.
Yeah. So a regular 20-gon would have 20 rotations and 20 reflections. There's actually a funny story. I think it was Gauss who discovered. I can't remember what he discovered. There was some property that he discovered about a regular 17-gon, about its constructability in some way, and he thought it was such a nice result that on his tombstone he wanted a regular 17-gon, and I think that the original person that he was going to hire to do that refused to do it because they said that I think the stonemason that was going to make it said it would basically look like a circle. But I think in the end, I think on his tombstone, I think that they etched it on the outer, it's like a surface, and then they did etch, I think, a regular 17-gon on it. Yeah, kind of peculiar, but yeah. So it'll have order 6, and this will be the case for other n-gons. I'll tell you in just a second, but the order will be twice the subscript because you're going to have 3 rotations and 3 reflections, so it'll be doubling that. Okay, so closure, that's going to be an essential component to an algebraic structure, which I'll define in a little bit, called a group. So that's something we definitely want. We want to have a nice operation. Another thing that we want is the property that there should be an element in there that has this property here. So notice that if I combine the rotate by 0 on either side of any motion, I'll just get back my motion. Basically, it's saying if I do nothing and then I do A, I'm going to get A back, right? And if I do A and I do nothing, I'm going to get A back. So what this do nothing motion is, it's behaving as though it's like an identity, which you're pretty familiar with. So in numbers, if you add 0, that's like an additive identity, right? You get back your number. If you multiply by 1, you get back your number. That's another type of identity. It's a multiplicative identity. And then another thing you would have seen in linear algebra, if I took a square matrix A and I multiplied by the identity matrix, you'd get A back. So you're pretty familiar with the idea of having an identity, but this is very general. So note an element with that property, you just call it the identity. And all groups must have one. So every group has to have one of these special elements. And another property that you want is, notice that for any motion A, there's going to be a motion B that will get you to that identity motion, the do nothing motion. So that is, there will exist a B for every motion A that will get you to do nothing. That sounds funny to say that out loud. It's kind of undoing the action of A. You call this the inverse element. So for every motion, there should be a motion that undoes that, gets you back to the identity motion. So for example, and we call them inverses of each other. So for example, if I rotate by 120, if I then rotate by 240, I will do a complete 360 rotation, but that is equivalent to doing nothing, so to speak, right? Because you're going to get back that exact same symmetry that you got by rotating by 0 degrees. Similarly, if I rotated by 240 degrees, then 120 degrees, that would also get me to R0. If you look in the Cayley table, okay, you can identify where the identity is, because if I were to combine the identity with any element, you'll actually just get a row that'll match what the elements that you're multiplying by are. So you see, I get this repeated row from up here. So I know that this R0 is my identity. That's how you can find it in the Cayley table. And then to find the inverses, pick an arbitrary element. So let's say E. Okay, to find its inverse, all I got to do is look for the R0, the identity element, and that's what I have to combine E with to get the identity back. So what this is saying is if I do the E reflection and then I do the E reflection again, I will get my R0, which makes a lot of sense, right? If I flip something and then I flip it again, I'm going to get back to doing nothing. So that's why every reflection will be its own inverse. But for rotations, that's not true, right? The inverse of R240 will be R120. And R120 will be R240, and R0 is its own inverse because, well, do nothing, I'm going to do nothing, right? So, okay, now this is another thing we have to have in every group, which is every element has to have an inverse, okay? And then finally, there is one other property that we will have to have, which is associativity. And if you're thinking back to function composition is associative. And it's not terrible to prove, but you remember in linear algebra, proving matrix multiplication is associative was absolutely horrible and horrendous. Yeah. In general, associativity is the most tedious and annoying thing to prove, but it usually is true most of the time. You can construct non-associative operators, and they are interesting for some applications, but most of the time, that's going to be a very quick thing to just check. And you'll see. Yeah, an additive version of it would yeah. I'll show you in a little bit. Well, yeah, actually to construct a non-associative finite collection, it's actually not as easy as you might think it is. It would look something like this. So let's say that I had A plus B plus C. It's really, all you're doing is moving the parentheses. So if you were talking about addition, it would look like this, A plus B, then plus C. Okay. So this would be associativity under addition. You don't have to write this down. I'm in the next note set, you'll see these properties written out. It's written in the very next note set. And then similarly, if you have multiplication, it would be like this. Okay. So you're not moving where the things are. That's not a commutativity thing. You're just moving the parentheses, which if you remember from linear algebra, vector spaces all have to be associative under vector addition. And vector spaces had a crud load of axioms. Do you remember that? It had like 10 axioms. And it had two. Yeah, well, it had 10 axioms and it had 2 operators. Groups are very general. You only have to have one operator. You have to have an identity, inverses, and associativity, and that's it. You have the binary operation, you have to have closure, but that's by saying it's a binary operation. The closure is immediate. But yeah. If you don't have an associative operator, it's quite general. And there are applications where those are useful, but you're pretty limited if you don't have associativity. Okay, so one thing we could take away from all this is the order of a group will just be the number of distinct elements in our group. And I'll formally write this out again later, but the order of a group is just how many elements are in that set, okay? So a group is gonna be a set with some additional stuff. So for example, the dihedral group of order 2n, where n is greater than or equal to 3. So it's at least gotta be a regular 3-gon equilateral triangle. You could have a square, pentagon, so on and so forth. And it will be the symmetries of the regular n-gon. We'll denote that as dn. And the order of that group will always be 2n because you'll have n reflections and n rotations. Okay. And another type of group that we'll see throughout this course is cyclic rotations of order n. So if you ignored the reflections and you just looked at the rotations, sometimes you have objects that only have a rotational symmetry. Do you remember back when you were a kid, you had those like pinwheel toys that spin? You know, you can take them outside and the wind will blow that thing. Yeah, I mean, actually, probably a wind turbine is similar. The symmetries of the fan blades on a wind turbine, they're going to be curved in such a way that you wouldn't be able to rotate it and get back the exact same object, but it can definitely rotate and give you the same object. I'll show you an example of that in just a second. The flag for Hong Kong is an example. So this flag here, right? The flag for Hong Kong. Yeah, if I reflect this, I'm not going to get the same thing, right? But I can rotate it, and do you see that because it sort of has it has C5 symmetry. So if I, instead of saying D5, so it has rotational symmetry, and it has these sort of 5 blades here, and they all have this star and the same exact pattern on the inside. So there's 5 distinct rotations that I could do, right? Like 360 divided by n, where n is the number of rotations that you can have. Okay, so it's, or you could just think of it as rotational symmetries of the regular n-gon. Okay. Now applications, I think I might have mentioned this before, but in understanding symmetry can be really important for a lot of applications, especially when you get down to very small scales. Okay, so for example, if you're a drug manufacturer and you want to produce things and on a mass scale, sometimes you'll produce a molecule in its chiral or mirror image molecule. And sometimes when you're doing testing, one of those can be very bad and one of them could be really good. Okay, so there's a whole area of chemistry devoted to exactly what we're kind of doing, which is called physical chemistries, or PChem, if any of you take chemistry. But they're pretty much doing group theory using, they have their own notation for everything, but they're pretty much just doing group theory, because it turns out that how certain molecules and chemicals interact on a very small scale can be determined by the types of symmetries that you have in that system, which is kind of interesting. Yeah. Yeah, it's kind of neat, all the symmetries that you get just from the molecules themselves. I mean, on a small scale. So this one, yeah, studying PTSD from organic chem, which is, yeah. Organic chem is a lot of memorizing, that's for sure. So here's kind of a molecular version of that little pinwheel toy that I was actually talking about. You see, it's pretty small. So this one has rotational symmetry. This one actually has reflexive symmetry, which is kind of interesting because of the nature of this. It also it's flat. A lot of times you'll have molecules where you can actually determine the angles in which those molecules are distributed, and that will highly affect the symmetries of what's happening there. So just wanted you to be aware, and there's a whole area of chemistry devoted to just understanding symmetries really well. All right. So there are lots of applications out there for this stuff, especially in physics as well. When you're doing things on a quantum scale, you have to understand symmetries really well, right? Okay, so hopefully that's kind of somewhat of an interesting introduction to what a group is, and hopefully you see that it in some way is encoding symmetries, or how you could potentially use this algebraic gadget to encode a symmetry. And throughout this whole course, what's kind of neat is every group that I tell you about describes the symmetries of something, and every object that exists can be, the symmetries of that object can be represented using a group, no matter how insane the thing is. Actually, the more asymmetric an object is, the simpler the symmetric group would be, right? Because if your object was highly asymmetric, then there would be no way to rotate it or reflect it other than probably the trivial one, right? So, but the more symmetries an object has, the more complicated the group might be. So for example, a soccer ball has, what does it have? It has hexagons and pentagons on the faces, right? So there's all sorts of interesting ways to move that object and produce a symmetry. Yeah, maybe I'll show you some of that as we go on. Maybe I'll show you some juggling math too. You can actually represent juggling patterns using all sorts of math too. Yeah, so we'll get to that a little bit later. You guys want a little couple minute break? No? All right. Let me just take a sip. No, I'm good. I just wanted some coffee. Okay. So now let's actually go through and define this stuff a little bit more formally. And we'll just spend a lot of time doing a bunch of different examples. So hopefully the definitions will be really clear. Okay, so binary operation on a set. So you give me a set. A binary operation will denote the very first time you ever see this with a star. Okay, so binary operation star on this set. It's going to be a function that assigns to each ordered pair of elements in the set a new element. Well, I won't say a new element, but it'll associate to an element of that set. Okay, so notation, you can think of it as a function from the Cartesian product of the set with itself, and so your input is going to be a pair. You give me two things, right? A pair, and then it's going to output an element of that set. Okay, so you give me a pair of elements, A and B, and you will combine them in some clever way. That's what that star means. You will combine them in some way. So you can think of this as it might be an addition, it might be a multiplication, it might be a rotation or some other weird method of combining these. Okay, function composition, whatever you want. Okay, but as long as it combines it in such a way that you get back an element of your original set, then that is what a binary operation is. Okay? Very general. So any crazy way that you can think of taking two elements, combine them, and get back an element of the set, then that is a legitimate binary operation. Okay. Now, if a binary operation star on G exists, then we say that G is closed under that operation. Okay. So here are some ways that you can have a binary. Here are some binary operations on the integers. Okay, so if you give me two integers, A and B, here are some ways that I could define my operation. Okay, if you give me two integers and you add them together, do we agree that that would be an integer? Yeah, so that would be a legitimate binary operation, right? You give me two integers, I can combine them by addition, and I will stay an integer, right? So addition is a binary operation. Subtraction is a binary operation, right? If you give me two integers and you subtract them, certainly it'll be an integer. If you give me two integers and you multiply them, that will be an integer. Okay. If you give me two integers, A and B, and let's say I multiply the first integer by 2, the second integer by 3, and then I add them, that will also be an integer. Okay. Keep in mind that if you're thinking of this as a function, I'm not asking the question whether or not it's saying onto. Is this note set on Blackboard? I thought I put it on Blackboard. Hang on, let me double check right now. I thought I added a week 3, but if not, I can, I think I have access to this. Oh, you know what? I have it on a USB and I can put it there. Okay. Week 3. Yes. If you go to week, so on Blackboard, oh wait, you know what? Maybe that's the problem. I made it. Maybe I didn't make it so you could see it. Okay, sorry. I think I just realized now. So week. Okay, let me switch to student view to see if you can see that. Okay, I'm sorry about that. Thanks for letting me know. Can you, yeah, thanks for letting me know. I just accidentally didn't share that link. Okay, cool. Sorry. Thanks for letting me know. I'm glad that you actually have these little pop-up windows when you guys talk. Because I was looking at the screen too, so I wouldn't have even seen that. Okay. Do you remember from linear algebra what this was kind of called? This is an example of a linear combination. Okay. Now, a linear combination in general is much more general because you can have those coefficients be any real number. But if we're trying to make sure that everything stays integer, that is one way that you could do it. I could take the first one, multiply by 2, second one, multiply by 3, and then add them. Keep in mind, you might not get every integer, right? So just like, do you remember when we were looking at onto functions versus what, like the range and the codomain? There may be some things that are skipped, but that's okay, all right? Now, when we talk about groups, groups will have some additional conditions to satisfy, so that might not happen. But one thing, right now, all I'm testing is if you give me these two things that are integers, is this result an integer, which is much more general, okay? Right now, I'm just testing if you give me two integers, is the output an integer, okay? I'm not testing identities and all that stuff just yet, okay? Now, if you give me two integers and I take one and add it to their product, that's also an integer, right? So there's many binary operations on the integers, okay? Maybe I should give you a non-example. If you, well, here's a non-example. Well, first of all, are these two binary operations, are these all binary operations on the real numbers?
Yep.
Yeah, if I add real numbers, that's real. If I subtract them, multiply them, do this, these will stay real. Rational, you have to be a little bit more careful. Just make sure that you could rewrite those as fractions, right? If I took two fractions, right, and I added them, I could rewrite that as a ratio of integers, subtract them, yes, multiply them. So you could confirm that as soon as you're taught in algebra how to actually do those operations, okay? Okay, well, what about, what if we actually rewrote this as maybe division or write it as A over B, okay? Now, if we're talking about the natural numbers, where natural numbers are positive integers, is this going to be a binary operation? No, right? And now to verify that it's not, all you got to do is just give me a counterexample, right? So for example, any, what about, yeah. What about 1 star 2? So this would be 1 over 2, and that's certainly not a natural, right? Now, sometimes it works, right? If I did 4 star 2, that would be 4 divided by 2, and that would be 2. So it does work for some of them, but as soon as it doesn't work for some pair, then it can't be a binary operation, because it says you need to be able to do this for any pair, okay, in the definition. Okay. What about real numbers? If you give me any two real numbers and you divide them, will it stay a real number?
Not if B is 0.
Yeah, not if B is 0. Good. So no. For example, let's do 5 star 0, which is 5 over 0. That is certainly not a real number, right? So this is undefined. Okay. Okay, well, what if I take out that problem? What if I consider non-zero real numbers? So one way you can denote non-zero reals or non-zero elements of a set, sometimes you can put a little superscript star, or you could just write it like this, right? R, and then we'll take out the element as 0. I think sometimes I also write it as, it looks like a subtraction, right? In the first day, we did some notation for that. But this just means remove the 0 element. So we'll have non-zero reals. What about there?
Yeah, I think so.
Yeah. Now we're not going to actually prove it, but if you give me, we know that if you give me two non-zero real numbers and you take the ratio, the only problem is when you have zeros in the denominator. So as long as you ignore that possibility, then it will be fine. And in this case, and it will stay a non-zero real number, right? There's no way to get, the only other thing that you would technically have to check is there a way to take A over B and get a 0 element, which is not going to be possible because then 0 would have to be in the numerator, right? Okay. What about positive reals? If you give me two positive real numbers and you divide them, will that stay a positive real number? Yeah. Yeah, right? The only way to get negatives is one of them would have to be negative, but you're choosing both A and B to be positive real numbers. So this actually works out as well. Okay, so that's kind of nice. Okay, how about this? Is the operation of combining them by addition is this. So A star B, let's say that that's defined as A plus B. Is that a binary operation on non-zero reals? No, why not?
If you choose any opposites, like 5 and -5,
Yep.
you get 0.
Good. Consider 5 star -5. Certainly 5 and -5 are non-zero real numbers, right? But if I add them, I will get 0, which is not an element of the non-zero reals. Okay. So you have to be very careful here to make sure, I mean, you're really just checking if you give me for any pair and I combine them in whatever way I define, as long as it stays in my set, then I'm okay. But things can get, somewhat complicated very quickly. Okay, here's an interesting example. So let Z3, so this is notation that we'll use for the integers 0, 1, and 2. In general, Zn will be 0 up to n minus 1. Okay, so Z3 we'll use for the set of 3 integers that goes from starting, the index starts at 0. So 0, 1, and 2. Okay, define this as the operation where A star B will be, let's take their addition and then we'll mod it by 3. Right? So is this a binary operation on Z3? So in other words, if you give me 2 elements in this set, you add them and then you mod it by 3, is it going to stay in there? Well, what happens when you mod it by 3? So thinking back to our division algorithm, right? That is going to be your remainder, right?
This is for computer science.
Yes, yes. Now, but from the division algorithm, we said that the remainder is guaranteed to be between 0 and n minus 1, right? In this case, n minus 1 would be 2. So you're guaranteed that that remainder is always going to be between 0 and 2 inclusive. So it'll be 0, 1, or 2. So the answer would actually be yes, right? If you give me 2 elements from here, and then I add them, and then I mod by 3, you'll be guaranteed this. Now, another way that you could check it is you could actually just go one by one through all of these possibilities. How many will there be? There'll be 9, right? Right. So 0 plus 0 mod 3 is going to be 0, right? 0 star 1 will be 1. 0 star 2 will be 2. Okay. And then I have 1 star 0 is 1 plus 0. 1 star 1 is 2. And then 1 star 2, 1 plus 2 mod 3 is 3 mod 3, right? And what's 3 mod 3? So remember how I was telling you when you're doing this modular arithmetic, you can think of it as subtracting or adding multiples of 3. So you could do division and then ask me what the remainder is. If I divide 3 by 3, the answer is 1 and the remainder is 0. So that's one way to do it. Okay, you get 0. But I think the best way to get it is to subtract until you get something that's a legitimate remainder. So if I take 3 and I subtract 3, I get 0, and that's one of my possible remainders, 0, 1, or 2. Okay. All right, let's go on to 2. 2 star 0 is 2. 2 star 1 is 2 plus 1 modulo 3 is 0. Okay, and then finally, what's 2 star 2? This is 2 plus 2 mod 3. Sorry that this is okay, so that's actually 4 mod 3. Okay, and again, you could do it both ways. The way you guys are saying you learned it in computer science is you take 4 divided by 3 would be 1, but then the remainder would be 1, right? Okay, so the answer is the remainder, which is 1. Or what I like to do is just take your number and what you're modding it by, you're going to keep subtracting until you get to a potential remainder. So if I take 4 and I subtract 3, I'll get 1, which is my remainder. Okay, that's how I like to do it. I don't know. Maybe you'll get a little bit faster at it. Like, for example, you keep subtracting until you get to a multiple of 3. Like for example, 22 modulo 3 is 1 because why? Well, 3 times 7 is 21, but then plus 1 will give me 22, right? So you could subtract 3 over and over and over again until you get 0, 1, or 2. Or you could do the division, which I don't know, maybe you still like to do it that way.
I guess that's how I did division in my head anyways.
Yeah. Yeah, any method is fine. I just think in terms of not having to do any division at all, there's a way about getting it without division. You can always do it with either subtraction or think of it as multiplication, I guess. I don't know. So always a way to get around. Oh, now one thing to check. The only thing we need in order to be a binary operation is every single output that we got, is that a member of Z3? Yeah. Right? Those are all the possible remainders. And in fact, you could have actually made this table, right? You could have made a table for this. You guys see this? You could have written 0, 1, 2, 0, 1, 2, and your star here is this modular arithmetic, okay? And 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, but modulo 3 is 0. 2 plus 0 is 2, 2 plus 1 is 3, but modulo 3 is 0, and 2 plus 2 is 4, modulo 3 is 1, which we're just writing. Do you see we're just writing these answers? So 0, 1, 2, 1, 2, 0, 2, 0, 1. And you get this nice little table. And this is, yeah, oh yeah, it's way faster, right? For sure. And this is the way you're going to want to do it. Okay, so that's the Cayley table for Z3. And you always verify it quickly by looking at the mod, in this case 3, and say, okay, the remainder. Basically, yes. Yeah. I mean, you could just look and see that. I'm just trying to start, take some baby steps, and we'll eventually get to those situations. Yeah. Okay. Next page. All right. In general, we'll denote Zn as the set of integers from 0 up to n minus 1. And the reason it's Z sub n, these would be the possible remainders if you were looking at the division algorithm and the thing you were kind of dividing by was n, right? These would be the possible remainders, okay? This will be a binary operation, the a plus b mod n will be a binary operation on Zn, okay? Similarly, I could ask about multiplication. So what about multiplication? If you took two elements of Zn, okay, and let's say I multiplied them together and then I modded it by n, the modular arithmetic says that that output has to be a remainder, right? And what are the restrictions? The remainder has to be between 0 and n minus 1. So won't the output of doing this be an element of Zn? Yeah, so this is also a binary operation. Okay, now we will see that this one will be very important, okay, for Zn. It turns out that while this one is a binary operation on Zn, it fails to make it a group, okay? So this one will be the more important one when we're talking about Zn, okay? It's not like we're gonna excuse this one. We're still gonna actually need to know how to multiply things and then mod it by n, but it'll be a different collection. It won't be that one, all right? It'll be related. Any questions? Maybe I should take a look at what you guys have been asking. Okay. Yes. Okay. Okay. Are we good? Okay. So now we know what a binary operation is on a set. What would a group be? A group, you have to have a set together with a binary operation on G, just like what we kind of went up above, but it has to satisfy the following axioms. So with groups, you only really have 4 things that have to be satisfied. Much more general than a vector space. Okay, so here we have to have, I call it the 0th property because I actually said it was a binary operation, right? But if you define something that's acting as a binary operation, you should always check, does it actually have closure? So one way to write that as a universal statement is something like this. It's saying for all A and B in your set, if I were to do that binary operation on the set, I will remain an element of that set. So that's one way to kind of write it as a statement that you could verify. Okay. First property has to have as associativity. So that's a property with 3 elements. Okay, give me any 3 elements of the set. If I were to do A star B and then combine that with C, I should get the same thing if I did A combined with whatever B combined with C is. Now keep in mind, I'm not moving where those things are. I'm just moving the parentheses. Okay. Second, well, it's the third property really. You have to have an identity element. Okay. And we discussed that before with that rotation by 0. Okay, so there must exist an element E. We'll call it E in your group. We'll call that the identity in the group, such that if you give me any element of the group and I were to combine it with my identity, I'll get back A. Right, and you should be able to combine that in either order. Okay, and then last property I have to have is inverses. For every element of the group, there must exist an element called the inverse of A, such that when I combine it with A, I will get the group identity. And notice I have to have a definition for the identity first, because otherwise you wouldn't be able to define what inverse even is. Okay, so they kind of go in order of precedence that you'll kind of check where it'll fail. All right, and that's it. So there are going to be many, 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 many things that are groups. Okay, now with vector spaces, you probably fell asleep by the time that the 10th axiom was given to you, but you had 2 operations on there. You had a vector addition, you had a scalar multiplication. They had to be closed, and then they had their own individual properties, and then they had a combination of the 2, which is the distributive law. Okay, so there were 10 axioms, and while vector spaces are general, they're not nearly as general as groups. In fact, every vector space can be thought of as a group under its vector addition. So groups, if you think of it as a huge circle, vector spaces are going to be a circle within that huge circle. Okay, groups are very general. So sometimes you may write this, you may write G, then comma star, just to signify, oh, I'm talking about this group, and here's the operation I'm talking about, unless it's clear. Like if I give you a certain group that it's not necessary to tell you what the operation is, then you don't have to write this. You could just write whatever G is. Okay. And one other thing, nowhere up here is it required that you have commutativity. Okay. There's nothing stopping that. There's nothing that requires that binary operation to be commutative. Okay, so we're going to have an additional definition that says if you have a group that in addition has this property, that if I do A and then combine it with B, it's the same as B combined with A, then we will call this an abelian group. Okay, so the group is said to be abelian or commutative, but most of the time if we're talking about groups, it's abelian. So abelian coming from Abel. Okay, Abel, a Norwegian mathematician. Yeah, so matrix, well, so if it was, so one example you've encountered before, yes, matrix multiplication is an example of a non-commutative type of operator, right? And another type is actually what we just did. This, if you look back at this table here, you'll see that this group, this dihedral group is non-abelian actually, because if I did, let's pick 2 things, for example. If I do n and then I do, let's say, let's do N and then R120, you get E. See that? But if I do R120 and then N, what do I get? So R120 and then N, I get the west one. You see that these are not equal? So that's a really small group too, right? It's only got 6 elements, and that one isn't even abelian. In fact, this is actually the smallest non-abelian group in existence. This one right here. You can't produce something smaller than that one that's non-abelian. So every group that's order 4 in the whole universe is abelian. All right. I just wanted to show you one example. But one thing, maybe you're looking up here and saying, if I look at this definition of inverses, it almost looks like I'm requiring A times B to be equal to B times A. Doesn't it look like that? But why is that not the case? Yeah, it's only in this specific, very specific situation. This is saying for all A in the group, there exists a B such that this property holds, okay? So if you do find an inverse element, it will commute with itself, okay? Or it will commute with its inverse, whatever it may be. But in general, down here, the property of commutativity is saying any pair, right? This is any pair. So for example, if you go back up here, what was the inverse of R120? If I rotate by 120, I got to rotate by 240 to get to my identity, right? So if I look at that one, R120, R240, they were inverses of each other, which gave me R0, right? But look at this. If I do R240 and then R120, well, these are inverses, so I should get R0. And you see, this is a situation where they actually are the same because they're inverses. But in general, that does not have to hold. Any questions so far? Okay. So this will be a very common thing that you're going to be checking is I might give you something and just ask you, is it a group? And these are the 4 things that you would show. So your template for proving something is a group is really just to verify that these 4 things are true. Right? And a lot of times, if the group is small, it's very easy to check these because you can just look at the Cayley table and identify all those things. Okay. Now, if it's very general, you're going to have to do a bit more work. Okay. Wait, what time? We go to 6:20, right? Okay. See, my other class goes from 11:15 to 12:05, and so whenever I end at the 5, but then we start at the 5, that's why I screwed up because never stop and start at a normal. Yeah. I mean, you'd have to, it would be shorter, right? It'd be like the graph theory one. Let's see. Okay. Next, let's just do a bunch of examples. So I call this the zoo of groups because I'm going to give you guys a whole bunch of examples of different types of groups. Okay. And I'll give you a nice chart in the end. So integers under addition, rationals under addition, reals under addition. These are all groups. Okay. Groups, right? The addition is a binary operation on the integers, which we mentioned, Q and R as well. Okay. The addition is associative. For now, I'm not writing out all the individual details. It would just take a very long time to do that. I'm just hoping at the moment you guys can agree with me with this. And we're not going to write out all the details just yet. Maybe if it was like a homework assignment, you would write out all the details for me, right? Like write out, let A, B, and C be an integer. Then of course, A plus B plus C with parentheses is equal to blah, therefore it's true. Okay, so it's associative. And what's the identity here? Under addition, if you give me an integer, what do you need to add to that integer in order to get back your first integer? Yeah, 0. Yeah. So 0 is your identity, is the identity. If I could spell. All right. Right. If A is your integer, a plus 0 is equal to a, which is 0 plus a, right? So for example, if you gave me 2, 2 plus 0 is 2, right? So that's your identity. What about inverses? The inverse of a is, yeah, negative a, right? Negative a is certainly an integer, since if I take a and I add it to negative a, I will get the identity. And that's the same if I add it in the other direction. 99% of the time, let's say 95% of the time, if you're dealing with addition, 0 or something 0-like is going to be your identity. Okay? And 95% of the time, if you have something where it's addition, the inverse is going to be some kind of form of the negative, whatever that may be. So that's something to remember. Okay, second example. Second example, let's go back to Zn. Remember, Zn is integers from 0 up to n minus 1. Okay. So this is a group under addition modulo n. Addition modulo n. Okay. For n greater than or equal to 1. Right? We just mentioned on the previous page that this definitely is a binary operation, right? So, right, addition mod n is a binary operation on Zn. Right? In other words, Zn is closed. That's another way to say it, under addition modulo n. And it's also associative. Okay. And that actually is inherited by addition on the integers. Because if you think about it, if I have the proof for this would be pretty short. It's just a lot of writing. If you give me 3 elements in here, a plus b plus c modulo n is the same as a plus b plus c modulo n. The reason that these would be equal is actually because addition of the integers without the modulo n is associative. So it's actually a property that's inherited from sort of a larger collection. All right, what is the identity of this group? Now this group is interesting because it behaves like the integers, except it's a finite collection instead of an infinite collection. So that's why this group will be very interesting for us. Okay. What's the identity here? Well, you remember I said that 95% of the time, if you're dealing with any kind of addition, the identity is going to be 0 or 0-like. And in this case, if I took the element 0, which is in here, and I added it to anything, and then I modded it by n, you're going to get back what you added the 0 to, right? So 0 will be the identity here. Okay. And now, here is where you have to think a little bit. What are the inverses? Yeah. Oh, good. Right. So if I gave you 1, for example, if you added n minus 1 to 1, you would get n, but then modulo n would be 0, right? Okay, good. So the inverse, yeah, of a in Zn is going to be n minus, well, I mean, it's not perfect because let's say that you picked a non-zero, right? Okay, well, I mean, it basically will work, okay? N minus a except 0, because n minus 0 would not be in Zn, right? 0 is its own inverse.
Okay, as long as
Yeah. But if you put a little mod n after this, then it's technically correct. Is that okay? Except 0 is its own inverse. You could actually write that it's negative the element, right? Negative a modulo n is n minus a, right? If you think about it, right? Because I would have to, the negative of this thing, in order to get, like for example, 1, negative 1 is not in here, right? But how do I make it so it is something in here? We'll just add an n to it. And then I have n minus 1. Kind of weird, right? Remember when you're doing modular arithmetic, wherever you are, everything that you either subtract multiples of n or add multiples of n will be equivalent to it, right? So if you were at negative a, if I were to add n to it, let's say you're non-zero. So let's say you're negative 1. That would be, if you add n to it, that would be n minus 1.
okay.
Right? All right. Maybe I should write it this way. Let's write it this way. Look, a plus n minus a modulo n, right? So now this is confirming if I took a and I added it to n minus a. If you put the mod n there, you don't have to add this little exception, right? Then this will be what? This will be n mod n. And what's n mod n? That's 0. Okay with this? The only thing is, the reason I had to add this exception is because if you wrote n minus 0, that's technically not in here. But if I put a little mod n after this, then it would actually be correct.
Nice.
Yeah. Are we okay with that? So writing, if you actually write negative a, that's still technically correct. So negative a is correct if you write negative a modulo n, because you actually would have to make sure that it's actually an element in Zn. And that is actually still a valid answer, because to get it so it is in Zn, you could add an n to it if it was non-zero, and then it would be that correct element. And this, remember, 0 is the identity. So that's why the inverse of a will be this. Okay. It's funny, every time I try to make modular arithmetic seem easier, I had to add this exception, so it might have made it more complicated. Okay, let's do some non-examples. The Zn will be one of the most important examples in this whole course, because it's like you should think of that as a finite version of the integers. And the integers, rationals, and reals under addition is also another very important example. But this one will be particularly important because of several properties that it has. Okay, so some other examples. So why are the following not a group? Okay, so first thing, what if I said the integers under multiplication? Oh, someone had a question. Now, to test whether or not that's a group, you have to go through all the axioms, right? So if you look back at the list of axioms that we have here. Okay. Now, if I'm the integers and I take two integers and I multiply them, is that still an integer?
Yep.
Yeah, so it is a binary operation. We said that before, so that's okay. Is multiplication of integers associative?
Yep.
Yeah, so that's not a problem. What would the identity be if if an identity exists, well, is there an integer that I could multiply any integer a by and get a back? Yeah, it should be 1. Okay, so far it looks like it's working, but what about inverses? No, right? Yeah. So for example, 2 has no inverse. Because you would have to come up with an integer to multiply 2 by to get the number 1, and
The only number with an inverse would be 1, right?
or -1. Yep. Yeah. Well, either of those. Right? Because -1 could work as well.
Yeah.
So anytime a group fails, you could actually perhaps fix it. You could think of what are some things I could do to modify that, and maybe it actually will work. So maybe if you just took the group of +1 and -1, those are the only ones that had an inverse, right? And I allowed multiplication. That would actually be a group. That's actually sometimes called the sign group. Look, like if I just took +1 and -1 under multiplication, then I'd have +1, -1, -1, and then +1. And now this guy is a group. It'll turn out that that group is actually the same as if I looked at Z2. And if you look at this, remember this was addition modulo 2. They're different in the sense the objects in there are different, but they are the same in the sense that they're sort of a translator that takes me from this world to this world, and they behave exactly the same. And later on in the course, we'll see that what you're actually saying is that there's an isomorphism between them. Okay, that's much later in the course, but it's like you're doing math in German here and you're doing it in French here, but you're doing it the same way. Okay. It's basically the same thing, except you have a bijection, but the bijection has to preserve the group operation instead of some structural thing. Okay, good. I think that's a good place to stop. But you know what? I could give you the other ones to think about before next time. Let's say integers under subtraction. Let's say Z6 and the operation is multiplication modulo 6. And let's say we had positive integers and under addition. Okay, so all of these fail in some way, and we'll pick up from there on, oh wait, it's Wednesday, right? Monday, I guess, yes. Okay. Yeah, right. Maybe if I could stick around for a few minutes if any of you had any last minute homework questions, or you can email me, but I think I made it so that it's due on Friday, so you can have a couple more days to think about it. Okay. All right. Well, have a good weekend then, I suppose. And I'll see you.
That on a Wednesday, right?
Sorry?
It's weird saying that on a Wednesday.
Yeah, I know, right? Because I won't see you again until Monday. All right, some questions. Yes.
Yeah, and when you take chemistry and organic,